Federated learning is a scheme that allows multiple clients to collaboratively train a neural network based on their individual data sets without requiring these clients to share the data by outsourcing the training process and that each client train its own model locally. However, the disadvantage of this outsourcing is that the server that coordinates this training process can no longer control the training, and such that a malicious client could actually try to inject a backdoor into the resulting model. I'm Philip Rieger from the System Security Lab of TU Darmstadt, and together with my colleagues Tienduk Nguyen, Markus Mikkinen, and Amatres Sadeghi, we developed a scheme that mitigates such backdoor attacks by analyzing the parameters of the individual neurons. But let's do first a small recap of how federated learning works. In federated learning, as I already mentioned, we have multiple clients which are connected to a server. While in centralized learning, the local dataset of each client would need to be sent to the server. In federated learning, the clients won't share their data, for example, because the data are very sensitive. So to overcome this limitation, in federated learning, each client trains its own model locally, and after the training is complete, it sends only the trained parameters to the aggregation server. Here, the models of the individual clients are aggregated, for example, by averaging them, and then the resulting model is sent back to the clients, and the clients can continue their training for further rounds. This scheme has multiple benefits. First, it improves the privacy, because the clients do not longer need to share the training data. Second, it also provides a better hardware efficiency, because the computation costs of the training are outsourced to the different clients, such that also the whole training process is parallelized and the computation costs for the server are reduced. Finally, it also provides a performance boost for the resulting model, because now more data can be utilized. Unfortunately, there's also a drawback of this, because in federated learning, the training processes are outsourced, such that a malicious client could actually try to poison the data and inject a backdoor, not just to the local model, but also to the aggregated model. And after this model is distributed to the clients, the backdoor will now also be part of the model that is available on every single client. Examples of how such a backdoor could look like actually includes, for example, in case of an autonomous driving car, a neural network that just mispredicts the speed limit signs, and such that all traffic signs that allow only 30 kilometers per hour are now recognized as allowing at most 80 kilometers per hour. To be honest, I don't want to sit in such a car. Another example of an application that uses federated learning is our mobile keyboards, for example, for word suggestion on mobile smartphones. Here, an adversary could inject advertisement to the suggested words. One more other application of federated learning uses it to analyze the network traffic of IoT devices to identify IoT devices that are compromised by malware to create a blind spot for a certain malware. To be honest, none of these three examples are actually desirable, such that there exist already a number of defenses to mitigate these attacks. These can be categorized into two different categories. First, approaches that try to prevent that the aggregate models, that the poison models are used for the aggregation, and second, approaches that accept that some of the models that they aggregate are actually poisoned, but they try to limit the impact of the individual updates to prevent that the poison model updates actually have an effect. For the first category, there exists a number of approaches that use clustering. Here are two examples that use k-means and HTB scan to separate the models into multiple clusters and use then one of them as a benign cluster for the aggregation. The second approach tries to prevent using poison models for the aggregation by selecting parameters that are for sure benign. So, for example, by using the parameterized median for aggregation, it tries to select a value that is for sure benign, or crumb, for example, assumes that the majority of clients is benign, such that it selects a single model as aggregated model that minimizes the distances to the other models. The disadvantage of this concept is that the data of different clients can actually differ from each other. So, for example, in case of the word suggestion, different users may type different texts, and then the model updates differ, and some of them might be excluded as outliers. But this means that the aggregated model is never trained on the data of these clients because their models were always excluded, and such that the resulting model will not perform well on the data of these clients. For the other categories, some examples are, for example, differential privacy, which have been shown to also reduce backdoor impact by adding noise to the models and also restricting the distance between the local models and the original global models that we started from. Another example, fool's gold assumes that the data of different benign signs differ significantly, and the data of poison models are very similar to each other. Therefore, it low rates similar models. The problem of this approach is that it can be circumvented. Differential privacy can be circumvented if the adversary focuses on the backdoor, therefore uses, for example, a high amount of training samples for the backdoor behavior in the training data, and fool's gold can be circumvented by just making the poison models different from each other. To address these problems, we designed DeepSight. But let's first start with some observations that we made for motivating. First, we observed that the backdoor data are usually focused on few different samples. So if we compare it with the benign data, for example, for a word suggestion system, the model needs to learn a whole language consisting of many words, lots of grammar rules, and so on, while the backdoor consists just of a few words in always the same order, such that here the backdoor is way less complex than the benign task. Secondly, the attacks are most effective with a high amount of backdoor data. Therefore, if the backdoor is strongly trained, if the adversary uses, for example, only a small amount of samples for the backdoor behavior, such that the trained model is barely able to switch towards the backdoor predictions, then if this weakly trained model is then combined with the benign models, the impact of this backdoor will become negligible, such that the attack is not effective. Of course, the adversary could actually compensate this weakly training by upscaling the models, such that when averaging it with the benign models, they have a higher impact. However, this can be actually mitigated by just constraining the maximal distance between the local models and the global model. The last observation that we made is that the data of different benign clients can actually differ because the users may have a different behavior, and analogously, also the data of malicious clients can differ. If, for example, if the adversary mixes the training samples for the attack behavior with training samples from the benign behavior to make the resulting models less suspicious. Let's now look on how DeepSight actually works. DeepSight takes the model updates and then first applies a filter. I will explain on the next slide in more detail how this filtering works. But for now, let's continue with the filtered models. Here we apply clipping to prevent the adversary from boosting the attack impact by upscaling the model updates. So surviving clipped models are then aggregated, and this aggregated model is then sent back to the clients. Let's now look on how this filtering actually looks like. For the filtering, we start with the individual clients. They train locally a model on the private data. When the training is finished, we want to distinguish the poison models from the benign models. Of course, the best option would be if we could just inspect the local training data and then check whether they contain backdoor samples. But the clients won't reveal this data for privacy reasons. So we need to take actually the second best option, the models that are trained on this data. Here we invented two techniques to actually analyze the models for information about the used training data. The first technique, the NOIPs, look on the distribution of the update for the neurons of the final layer. These neurons actually represent for each a category. So here in this example, we have 3 neurons in this final layer, such that the neural network takes a sample and then predicts to which of 1 out of 3 categories the sample belongs. So if we just take the distribution of the updates for these neurons, then we get some information of how frequent each category was in the training data. And by this, we can create a fingerprint. The second one, the second matrix that we invented, takes a look on the probabilities that the neural network predicts. When it takes an input sample, it predicts for each category a probability that this sample belongs to this category. So if we train the neural network on the local data, also the probabilities changes, and these changes are analyzed by the second matrix called DDIFs for creating a second fingerprint. So DeepSight now just receives the model updates and then creates, extracts all these features. So for each feature model, we have the NOIPs, the DDIFs, and as a third metric, we also calculate the pairwise cosine similarities, therefore the cosines to all other models. We use all the 3 features for the clustering in the second step, but the classification that I will explain now will uses only the NOIPs. As I already explained, we observed that the training data for the Backdoor consists only of few different labels. Since the NOIPs actually show the distribution of the labels in the training data, we can use this to analyze the models. If a model has NOIPs that focus only on few neurons, then this is very suspicious. Then we label this model as most likely poisoned. Here in this example, we had 2 malicious signs. One which was trained strongly for a Backdoor, signs that had many samples, and one which was only weak. Unfortunately, the second one is not detected here. But for this reason, we also have the second step, the clustering, which uses all these 3 fingerprints and then performs a clustering. In the final step, we combine both results, therefore the labels and the clustering, and count for each cluster how many models in this cluster were poisoned. And if more than 1/3 of the models were poisoned, we just exclude all models inside of this cluster to compensate some false negatives. And then we forward to surviving filtered models. Let's now look on how DeepSight actually performs. Here we have a comparison of DeepSight with a baseline without any defense. For this, we calculated the Backdoor accuracy, therefore the accuracy of a test set containing only samples for the Backdoor behavior. And secondly, we also calculate the accuracy on the benign main task. To check how well it distinguishes benign and poisson models, we calculate precision and recall. The first data set, MNIST, contains of handwritten images and is a standard benchmark dataset. As you can see, the Backdoor accuracy without defense is very high, while the main task accuracy drops from around 96% to 58.9%. In comparison, DeepSight mitigates the attacks, the Backdoor accuracy is almost 0, and the main task accuracy remains at 96.6%, while it perfectly distinguishes benign and poisson updates, as precision and recall is 100%. The second application considers a natural language processing scenario, for example, word suggestion. Here we use the dataset consisting of Reddit posts, and again, the Backdoor accuracy is 100%, while the main task accuracy is 22.4%. Please note, NLP is a very complex application, so for this reason, the MA is even without attack, but only 22.6%. DeepSight completely mitigates this attack. The Backdoor accuracy is 0, while the main task accuracy remains at 22.6%, and it perfectly distinguishes. The last application is a NIDS application that I mentioned in the beginning. Again, Backdoor accuracy and main task accuracy are 100% without defense, while DeepSight mitigates the attack and distinguishes the models. Of course, this was only a small excerpt from the evaluation that we performed. So if you want to have a closer look on the evaluation, feel free to have a look on the paper. Thanks. Any questions?